Okay, one comment on the homework. The second homework is already, I haven't published it yet, but it's uploaded. I'm going to experiment with something, okay, about submissions. I realized as the week wore on that the email thing, like a lot of people have emailed me their homework. That's cool. That's totally fine, PDF. And I'll forward that to whatever TAs are grading the problems. However, given the size of the class, that's probably going to get pretty cumbersome after a while, for me to keep track of all these emails and forward them all. And last spring we had a big class. It was okay, but this semester, because I have this other class, it's kind of like I'm thinking, okay, I'm going to figure out a more efficient way for this. So there is a way to enable PDF file upload on Canvas. Have you guys done that in other courses? Okay, on the second homework assignment, I went through the steps to enable that, and I want to test this as a test run. So I will, note that on the publication of the homework that I'd like to see those of you who would like to submit electronically do it that way rather than email it to me, and we'll see how it goes. Okay, just so you know. All right, so anyway, last time, remember we took our first baby step in the direction of Fourier series, and that was the following. We saw that if x of t is a real valued signal that's the sum of a bunch of pure sinusoids, and by the way, real valued finite sum, so there's only a finite number of terms, finite sum of sinusoids with what I called harmonically related frequencies. That just means that all the frequencies, if you take any two of them, take the ratio, you get a rational number. Then we can find numbers a sub k such that x of t is equal to the sum from k equals minus n to n. And let me just say you can find numbers n and ak. And these guys might be complex. Such that x of t is equal to this, ak e to the jk 2 pi f0 t, comma, where f0 is equal to the greatest common integer divisor of all the terms frequencies in x of t. And that turns out to be the fundamental frequency of x of t. And that's just going to be the GCID of all terms frequencies. And the real valuedness of x of t, so furthermore, you have this conjugate symmetry, namely a sub minus k is the complex conjugate of ak for all k. Okay, so finite sum of pure sinusoids with harmonically related fundamental frequencies can be written in this fashion. And this expression here for this particular kind of signal, this is the complex exponential Fourier series for x of t. Now, all of you, as I learned last time, saw either in your multivariable calc or differential equations course Fourier series in sine and cosine form. This, it turns out to be a lot cleaner if we write them this way. It turns out to be figuring out the AKs, all that stuff is a lot easier. So that's why I like to do it this way. So this is for x of t. Now, this is like a mini theorem. Called it a mini theorem last time. It turns out that essentially any well enough behaved periodic signal x of t can be written in this form, but with an infinite number of terms. Okay? So it turns out that a much more general result holds. Namely, and this is, you might want to call this the Fourier Theorem, quote unquote Fourier Theorem. If x of t is a reasonable, and I'll tell you what reasonable means, a reasonable periodic signal, and I'm going to assume real valued here, with, and let's just assume it's not a constant, just to make it non-trivial, fundamental period t0 and fundamental frequency f0, which is just 1 over t0, then you can find possibly complex numbers, a sub k, such that x of t can be expanded in the following fashion. And the meaning of what I mean by can be expanded in the following fashion, we are going to have to get very specific about that later on. K equals minus infinity to infinity, ak e to the j k 2 pi f0t. Okay? Now this thing we will talk later in more detail about what this equality means, namely how this series converges. But one other additional comment, we can tack on that furthermore thing, that because x of t is real valued, the AKs have a conjugate symmetry. So furthermore, a sub minus k is equal to ak conjugate for all k. So the difference between the mini theorem and the big theorem is just the extent of the sum. The mini theorem applies to periodic signals, real value periodic signals, that are finite sums of pure sinusoids. And by rearranging and reindexing things, we can always write it that way. The big theorem applies to arbitrary periodic signals that are reasonable, in a sense to be made precise later. All right, so anyway, first of all, I'm going to tell you, how do you get the AKs? And then we're going to go through some examples, talk about some intuition about these things. Has anyone seen this complex exponential form of the Fourier series before in some context? Yeah? Jack, is that right? Where?
In my waves class.
Waves class. So is that physics 2218 or 14?
2218.
2218, yeah. Did you take 2218?
I took 14.
You took 14.
And I'm pretty sure we did complex exponential form of this as well.
Yeah. Well, the math is so much cleaner, in my opinion. I don't know. So anyway, so here's the question. How do you get the AKs? First off, how do people present you with the signal x of t? Generally, it's going to be a graph or a time function with an explicit t dependence. So in this case, so generally, x of t is sort of presented as, say, a graph or some explicit function of t. And in principle, you can move back and forth between graphs and explicit functions of t. Like, for example, somebody might draw a triangle wave or a square wave or a sawtooth wave that's obviously periodic with some period t0 and some frequency f0, and ask you to write x of t that way. Anyway, given such a presentation of x of t, how do you find the AKs? So how, given such a presentation of x of t, do you find the AKs? Now, contrast this with a mini-theorem. The mini-theorem, someone comes up to you on Hochplaza or whatever and gives you a finite sum of sinusoids with some BLs, you know, whatever. That's the notation of the class last time. And says, please, you know, I really want to write it in this form. And all you have to do is rearrange, reindex, blah, 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 and you get that. That's one way of having a signal presented to you. But this is the more common way. You know, you have data and you have this periodic thing going on, you know, that looks like something. And you want to figure out the AKs like that. All right, so how do you do this? Here's the derivation of the formulas. So all of it is based on this basic fact. The basic fact goes like this, that if I take the integral, so this is given t0 bigger than 0, and f0 equals 1 over t0. If I take the integral from 0 to t0 of e to the j, and let's call this L 2 pi f0t dt, and divide that by t0, I get 1 when L equals 0, and 0 when L is not equal to 0. And here L is an integer, positive or negative. All right, now why is that the case? What if L equals 0? What is the integrand in that case when L equals 0? 1, yes. 1 times dt. If you include dt in the integrand, it's cool. Depends on where you were trained in calculus, whether you can include the dt. All right, so it's 1 dt integrated from 0 to t0, divided by t0, boom, you get t0, you get 1. Why is it 0 when L is not equal to 0? Let's do the integral out. Just make sure we're on the same page here. So this is clear what happens when L equals 0. When L is not equal to 0, we get, when we integrate the thing out, we get 1 over t0, integral from 0 to t0, e to the j L 2 pi f0t dt equals 1 over j L 2 pi f0 t0 times e to the j L 2 pi f0 t evaluated between t equals 0 and t equals t0. And that becomes 1 over jl 2 pi. And by the way, f0 t0 is equal to 1. So because f0 t0 equals 1, times e to the jl 2 pi f0 t0, which again is just jl 2 pi in the exponent, because f0 t0 is 1, minus 1. Why is that equal to 0? Yes. E to the j L 2 pi minus 1 is 0. Anytime you take, this is something, again, I can't hammer this one home hard enough. When you take e to the j integer multiple of 2 pi, you always get 1. All right? So this becomes 0. And why does this argument fail when L equals 0? It fails because I'm dividing by 0 here. So that's why I have to consider the L equals 0 case separately. Got it. Good. All right. So that basic fact enables us to figure out the Fourier coefficients, A sub k for x of t. So let's apply this as follows. All right. So our goal is to figure out all the coefficients in a Fourier expansion. Let's just say x of t equals sum from, and I'm going to use m here, equals minus infinity to infinity, a sub m e to the j m 2 pi f0t. So we want to figure out all the a sub m's. First thing we're going to do is we're going to integrate both sides of that equation from 0 to t0. And divide by t0. What do we get? On the left-hand side, we get this. We get 1 over t0 integral from 0 to t0 x of t dt. And remember, the x of t has been presented to you as an explicit function of t or maybe a graph. So you can figure out what that is. What do we get on the right-hand side? Well, we get this. We get the sum, and I'm being play fast and loose with integrating, interchanging integration and summation and all that kind of stuff. We get a sub m summed over, and we're going to have 1 over t0 integral from 0 to t0 e to the j m 2 pi f0t dt. All right, so in the parentheses, we have a thing that plays into the basic fact, right? This is going to be 0 when m is non-zero and 1 when m equals 0. So this parenthesized thing is 0 when m equals 0 and 1 when m is not equal to 0 by the basic fact. So what does that mean? On the right-hand side, that means you have, it's an ostensibly infinite sum of things, but infinity minus 1 of them are 0, okay? And only 1 is non-zero, possibly, right? So what this whole thing looks like is dot, 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 plus 0, plus 0, plus 0, plus a0. That's the only one that has a non-zero thing multiplying it, plus 0, plus dot, 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 dot. It's like a sum of a zillion zeros flanking an a0 in the middle. Everybody see why that's the case? Bottom line is that we figured out a0. That's the first step, or the 0th step in figuring out all the a's. a0 equals 1 over t0 integral from 0 to t0 x of t dt. That's our first formula. Yeah.
Sorry, I think in the basic fact you have written 0 when m equals 0 and 1 when m not equals 0 is switched.
Oh, clearly this is 1 up here and a 0 down here. Is that why there was confusion in the room or not? See, I was trying to catch the people at home. You know, I'm going for 100 views per lecture, so just tune in for a couple minutes. Counts as a view. If I get 100 views, everyone gets 1 extra grade point. No, it's like, all right. OK, so modulo that correction, right? We're good. Are we? This is cool. a0 equals that. Now, again, remember, x of t is presented to you as a graph or as an explicit function of t, so you can figure out this integral. And the only thing that's a proviso here is that x of t is nice enough to integrate. OK, so that's going to be part of the reasonableness. Remember, I told you I was going to elaborate on what it meant for something to be a reasonable enough thing to do. You're going to have to be able to integrate it. All right, now, more closely, we look at that formula, we see, OK, so what is a0? a0 is 1 over the period times an integral over the period of x of t dt. So what's a name for that? What do you, when you integrate a function over an interval and divide by the length of the interval, what do you get? Yeah. The average value of the function over that interval. And if it's a periodic thing, right, you're getting just the average value of the whole function over all time, right? So note that A0 is the average value over one period, and hence over all time, of x of t. So the zeroth Fourier coefficient is always going to be the average or the mean value, whatever you want to call it. And ECEs have slang for average value of a signal. Do you know what that is? You must know that. Come on, you guys must know what this. The slang for the average value of one of these things. Jordan?
Bias.
That's CS slang. You should have known coming from a closet CS guy. Okay. All right. So what? He actually what? You were a CS undergrad, weren't you? Yeah. And so it's not. He's out. All right. So what would be an ECE slang for the average or mean value of like a voltage signal, say? See? DC. Who said that? Thank you. This is what people also call. I stood still in front of the camera while you were gone, so it's called a DC value of x of t. So, you know, ECEs talk about things like, well, this filter kills DC, or it passes DC and it kills high frequency, you know, things like that. So ECE slang. A0 is the DC component of the signal x of t. Very good. Okay, so that's just A0. What about the other AKs?
Question.
Yeah.
Sorry. So does
No.
EC here stand for direct current or not?
Direct current. Yeah. Yeah.
How does that?
No, it's just slang. It's like I said. It's not. It's there's no physical reason to call it that except for slang, kind of. You know, I don't know. The Tesla is all the rage right now. The guy, not the car. You know, so you know you can. There's a movie coming out about him, or it's already come out. I don't know, but there was this famous dispute between Tesla and Edison about whether to use AC or DC as the, you know, house current, that kind of thing. And so there's a whole body of legends. It's kind of like Middle Earth, you know, around DC and AC and everything. All right, next step, let's figure out the other AKs. So as for the other AKs, what do? Well, we take the expression that we have for x of t, this one here, and we multiply both sides, and I'll give this equation here a name. Let's call it double star, because I already used up star on something else. So you multiply both sides of double star by e to the minus jk 2 pi f0t, and you take the result and you integrate 0 to t0 and divide by t0. And what do you get? On the left-hand side, you get this. You get 1 over t0, integral from 0 to t0, x of t, e to the minus jk 2 pi f0t dt. And on the right-hand side, playing fast and loose with interchanging integration summation, you got this. The sum from m equals minus infinity to infinity of a sub m times 1 over t0, integral from 0 to t0, e to the j m 2 pi f0t times e to the minus jk 2 pi f0t, which is e to the j parentheses m minus k 2 pi f0t dt. And this is essentially the same thing we had when we were figuring out a0, except it's kind of shifted. The thing in the parentheses here, by the basic fact, is, and I'm going to get it right this time, it's 1 when m equals k and 0 when m is not equal to k. So the parenthesized thing on the right-hand side is 1 when m equals k, 0 when m is not equal to k. So 1 over t0, integral from 0 to t0, x of t, e to the minus jk, 2 pi f0t dt equals, again, a slew of zeros. The only thing on the right-hand side that could conceivably be non-zero is the m equals k term. So you're going to have dot, 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 plus 0, plus 0, plus ak, plus 0, plus 0, plus 0, dot, dot, dot. And that's just equal to ak. Bottom line. ak equals 1 over t0, integral from 0 to t0, x of t, e to the minus jk, 2 pi f0t dt. And this is for when k is not equal to 0. The two circled formulas give you all the AKs. And in fact, this one even works when k equals 0 to figure out a0. But I always like to separate the computation of a0 from the other AKs because it shows what a0 is. It's the average value of x of t. And that's something you want to pick up right away, that if you have a periodic signal and you expand it in a Fourier series, the 0th term of the Fourier series is the average value of that signal. And that's why I like to separate out the computation of a0 from this. And again, x of t is presented to you as an explicit function of t or a graph, meaning you can do this integral, or at least approximate it, or look it up or something, just like you could do the integral for a0 and figure out the AKs from it. All right, now before we do examples, before we do a couple of examples, I want to do like a minor comment. And this is just a work saver. So here's a comment. It turns out that we can do these circled formulas for the AKs, and we don't have to necessarily integrate from 0 to t0. All we have to do is integrate over any interval of length t0. So you can evaluate the a0 and ak formulas by integrating their integrands over any t0 interval, not just 0 to t0. And this might save you some work if x of t is expressed in such a way that the integrals are easy to do over an integral other than 0 to t0. But I just want you to know that. And we have notation to go along with this. Notation that I like to use, and this is my own invention, so I don't know if you don't like it, fine. If I write integral sub t0 of whatever dt, that expression means, quote, integral over any interval of length t0 of whatever. And this is a well-defined thing precisely when whatever is periodic and t0 is a period of x of t. So this works when whatever is t0 periodic. Okay, so we could re-express those formulas for A0 and AK in that form using that notation as well. All right, so very cool. All right, so let's do an example. And maybe before doing that example, let's hark back to the mini theorem, the thing that applied to signals x of t that were finite sums of sinusoids. If you did this whole integral process for finding the AKs for those signals, you would get the same answers you got just by doing the reindexing and rearranging that we did last time. All right, so another comment is that if x of t is, like last time, a finite sum of sinusoids, and you followed these formulas here, so you apply the circled formulas to x of t, you get the same AKs the same Fourier coefficients that we got last time just by reindexing, rearranging, etc. And nobody wants to do all that integral work for the circled formulas involving products of cosines with complex exponentials and all over the place when you can just do rearranging. So some people say, like, wait, I have this formula for Fourier coefficients, and then we have the rearrangement thing last time. In these cases, those two approaches lead to the same A's. Okay, so in these cases, for these x of t's, there's no need to integrate, all caps, to find the Fourier series. All right, but here's a canonical example where there is a need to integrate. And this is straight out of the book. So here's one where you do need to integrate, but the integration is easy. All right. This is an x of t that looks like this. It's going to have, here's t0, here's 2t0. These are all supposed to be the same, by the way. Dot, dot, dot. Over here you have minus t0, minus 2t0, dot, dot, dot. And these are all going to be, for now, they're going to be height 1. And they're all going to be width tau. And they're all going to be centered on the integer multiples of t0. So this point here is going to be tau over 2. This point here is going to be minus tau over 2. And a signal like this, there's a name for signals like this. It's called a pulse train. Come up all the time in applications. Let's figure out. Clearly, it is periodic, right? OK, that's what the dot, dot, dots mean. The ellipses. And what is this fundamental period? Graph is labeled suggestively. What is this fundamental period? T0, yes. Excellent. You shift it by T0, you get the signal back. And there's no smaller value of T0 by which you can shift it and get the signal back. All right. So let's figure out its Fourier coefficients. First off, what is its A0? A0. Now, without doing any integrals at all, you know that A0 is the DC value or bias of this signal, right? So what is the DC value of a pulse train with period T0 where the pulses have width tau?
Is it, I want to say tau over T0.
You're right. You're exactly right. It's tau over T0. Like the smaller tau is, the smaller the average value of this thing is, because it's only 1 for tau every period, right? So A0, this is just the average value or DC value of x of t, and that's equal to tau over T0. And you can do this, you can do the integral. You can formally calculate that just by integrating 0 to T0. And by the way, this is an example where it's easier to do this, figuring out the AKs, integrating over a different interval from 0 to T0. So let's figure out the AKs. For other k's, AK is going to be equal to 1 over T0 times the integral. And what interval, if someone came up to you, well, no, they wouldn't even know what an integral was. I'm trying to imagine the situation. If you saw this thing and you were told that you could pick any interval of length T0 over which to integrate this integrand, what interval would you pick? Yeah.
Minus t naught over 2 plus t naught over 2. Or possibly tau over 2 and t naught plus tau over 2.
And that's because in that interval you only have one sort of thing. You have like if you integrated 0 to T0, you would have 1 for a while, then 0 for a while, then 1 for a while. But if you integrate, say, this one, minus T0 over 2 to T0 over 2, you just have 1 for a while in the middle, and it's more symmetric. So I'm going to actually use your first suggestion. So I'm going to let this be minus T0 over 2, and this be T0 over 2. And use those as, you'll get the same answer anyway, either way you do it. But this just makes it come out prettier, or come out quicker. So note, I chose the T0 interval over which to integrate. And it's not necessarily 0 to T0. Let's do the integral out. What happens? One of these is a much nicer eraser. You get a sub k equals 1 over T0 times the integral. And integrating from minus T0 over 2 to T0 over 2, nothing contributes for little t between minus T0 over 2 up until you get to minus tau over 2. So that's what I get from my reduced limits of integration. And in that zone, x of t is equal to 1. So the integrand is just this. And now we just blindly integrate. So we get minus 1 over j 2 pi f0 t0 times this thing evaluated from minus tau over 2 up to tau over 2. So I get e to the minus j k 2 pi f0 tau over 2 minus, we're going to do the 3-minute break after I'm done with this calculation, so don't worry, e to the plus jk 2 pi f0 tau over 2. That whole thing. You can simplify that as follows. f0 t0 is 1. So this just becomes a 1. Inside the parentheses, what have I got here? I've got an Euler thing. This guy inside the parentheses is equal to minus 2j sine of k 2 pi f0 tau over 2. The 2's cancel. The minus signs cancel. These 2's cancel. And the bottom line is you get sine of k pi f0 tau divided by k pi. And that's for all k not equal to 0. And let's take the 3-minute break, and I'll make sure that's right, and then we'll talk about it some more. OK, so anyway. So here's an example. Here's an example of figuring out the Fourier series coefficients of this x of t. X of t is presented to you as a graph. It's easy to do integrals based on that graph in this case, and we get these. And so let's look at a couple of general observations about this. One thing is the rate of decay of the Fourier coefficients as k goes to infinity. In this case, by the way, all the Fourier coefficients turn out to be real numbers. I told you that in general they're going to be complex numbers, but here they turn out to be real numbers, just by virtue of how the signal is. So that's one thing to note. In this case, in this particular case, all the AKs are real. Not so in general. And you can actually show that if you have a real valued even function of t, then you're going to get real Fourier series coefficients. But I'm not going to worry about that as a thing. Another thing, what is the rate of decay as they go to infinity, as k goes to infinity? The AKs go to 0, quote unquote, like 1 over k as k goes to infinity, plus or minus infinity. And that's pretty clear from the formula. And 1 over k is not a particularly fast rate of decay, as you may know or not know. So this is not a particularly fast rate of decay. It's not even fast enough so that like you can guarantee that the sum of all the coefficients is something that converges. But anyway, how does that in general play into signals analysis? Well, it turns out that the rate of decay of the Fourier coefficients has to do with how smooth the function is. The spikier and nastier the function is, the slower the Fourier coefficients decay as k goes to infinity. So here's a general feature. Is that when you have x of t spikier, sharper, more discontinuous, more jumpy, then the AKs are going to go to 0 not so fast. The AKs don't decay fast as k goes to infinity. And the smoother x of t is, implies faster decay. And you can, actually, you're going to do this, I think, on the homework, or maybe they do it in the book, I forget. I'm not going to look right now. If you look at a triangle wave, so for example, if x of t is something like this, is a triangle wave, like so. It turns out, now this still has corners in it, right? But it's not, it doesn't have jumps like the pulse train. This guy has Fourier coefficients that go to 0 like 1 over k squared as k goes to infinity. So the AKs go to 0 as k goes to infinity, plus or minus infinity, like 1 over k squared. And that's faster than 1 over k. And if x of t is just a pure sine or a pure sinusoid or a finite sum thereof, then the AKs go to infinity in finite k, infinite number of k values, because there's only a finite number of terms. So they go to 0 infinitely fast, if you will. All right, so that's just a general feature. All right. And here's some terminology. If you have the Fourier series coefficients, so given the AKs, given x of t, and it's AK, and you find its AKs, we already know what we call A0. A0 is the average value of x of t. If you take the k equals plus and minus 1 terms together, we call this sum, namely a sub minus 1 e to the minus j 2 pi f0 t plus a sub 1 e to the j 2 pi f0 t. So the sum of the k equals plus and minus 1 terms, we call this thing the fundamental component of x of t. And we call, and here's where different books disagree on the terminology we use. And it's not a deal breaker, but all right, I'll tell you. Like, in Romance languages, right, you may know that, like in Europe, if you go to Italy or France or whatever, if you go to a building, they call the ground floor, they don't call that the first floor. They call that, like, something in French it would be the rez-de-chaussée. You know, it's like what you walk into with your whatever. And then they call the one right above that the premier étage, the first floor, right? So they call, in some sense, the ground floor is like the 0th floor, whereas in this country, the ground floor is the first floor. And some people, they say, OK, this is the fundamental component, and the k equals plus and minus 2 terms sum, which is going to be a sub minus 2 e to the minus j 2 pi times 2 f0 t plus a2. And let me write it the way it is in the, so j2 2 pi f0 t plus a2 e to the positive j2 2 pi f0 t. Some people say fundamental, and this is the first harmonic. OK, that's what they say. I don't say that, and the book doesn't either. This book doesn't either. They say, I call this the second harmonic, even though we don't have a harmonic yet. And the reason I call it the second harmonic is because I want to call the k plus and minus k terms the kth harmonic component. And so this goes so and so and so and so. A sub minus k e to the minus jk 2 pi f0 t plus e to the plus ak e to the positive jk 2 pi f0 t. We call this the kth harmonic component. Of x of t. And so on. Now, if you do the premier étage thing, you know, the rez-de-chaussée thing, you would call this the first harmonic and this the k minus 1th harmonic. I just think that leads to all kinds of crazy confusion. But anyway, you can notice we have this word harmonic creeping in. Okay, that's a music-y kind of word, right? And a lot of our examples of these periodic signals are going to be drawn from music. And next time we'll bring in the keyboard from the lab and play around with it a little bit. And maybe we'll test Alex's perfect pitch, right? Anybody here in band? It's either band, pep band or marching band or anything. Don't be embarrassed. No.
Join band.
Join band, yeah. Chalkings on the sidewalk, you know, every fall. Arrows pointing to Shuttlecock Field or whatever. Yeah.
Next week I'll wear my Boing Jan shirt.
Your Boing Jan shirt, yeah. Anyway.
We also have the orchestra.
Orchestra counts, you know, that's cool. Like one kid in 2200, Cornell Winds, you know, string ensemble. One guy in 2200 last fall played the viola in one of the string orchestras. He's a Mat Sci major who took 2200. Imagine why a Mat Sci major would take 2200. I don't know. But hey, okay. So we're going to be talking some about music, and these harmonic components are pieces of a signal, and you know, we can draw analogies between how harsh something sounds and how much energy there is in the higher harmonic components. If you talk about slowly decaying, so if you have the a sub k decay slowly in k, too many k's, that corresponds roughly to more energy, more signal energy in the higher harmonic components. And that's, in musical terms, that's going to be like more overtones and more, you know, harshness. Like a square wave synth, you know, square wave synthesizer sounds different from a triangle wave synthesizer. And it's a matter of which one sounds harsher or more mellow than the other, and that has to do with how fast the Fourier coefficients decay as k goes to infinity. So that's some general stuff about the Fourier coefficients and some terminology that we're going to be using a lot. I want to go back to the pulse train example, and so look at a variation on the pulse train example. What we're going to do is we're going to normalize it. We're going to normalize the heights of the pulses so that the average value, the DC value, is always 1. So we're going to normalize so the DC value, which is just A0, the average value, is equal to 1. And what that does, the one way to do that is just to multiply the whole thing by 1 over your answer, which is multiply the whole thing by T0 over tau. So take the original x of t and you multiply it by T0 over tau. Oh, I forgot to do one. Oh, forget it. Let me do an interjection here. I don't like to do this, but I'm going to do it anyway. So pause this for a sec. I just really quick want to look at, in the pulse train example, so pause. First, look at pulse train example when tau is exactly half of a period. So tau equals T0 over 2. So the thing is on half the time and off half the time, and it's equal to 1. That means its average value, A0, is 1/2. And when k is not equal to 0, ak is equal to sine of, what was it, k pi f0 tau divided by k pi, right? Now f0 tau is f0 cap t over 2. So that's sine of k pi over 2, because f0 t0 is 1 divided by k pi. And what's an easy way of writing sine k pi over 2? Well, it's not that easy. When k is even, it's 0. Right? Because you've got sine of an even, or sine of an integer number of pi's. What about when k is odd? What is that equal to? What is the num equal to, numerator? Sorry?
That will be 1. The numerator will be 1.
OK, what about when k equals 3? Yeah, so it's going to be -1 to something, right? It's going to be -1 to the k minus 1 over 2 divided by k pi. I told you it wasn't that easy. It's kind of easy when k is odd. See, this takes care of, like, when k is 1, it's 1. When k is 3, it's -1, right? K is 4, it's 1 again. Or, sorry, 5, it's 1 again. All right, but still, these guys are still going to 0 like 1 over k. So end pause. I meant to do this before I did this. And so I would get a error message saying there is no begin pause. So if that bothers you guys, let's fix that. All right. OK, so now let's go back to look at the variation of the pulse rate example, normalize so that the average value is always 1. All that does, takes the original x of t, multiplies it by tau over t, t0 over tau. That means that a0 equals 1. And then this is the renormalized version. ak is just going to be t0 over tau times the original formula for that. So it's going to be sine k pi f0 tau divided by k pi. Now, if I rewrite the f0, the t0 as 1 over f0, I get sine of k pi f0 tau divided by k pi f0 tau. Right? And this is just a sine theta over theta type of thing. And this is sine theta over theta. Whenever you can find it somewhere, it's your friend. It helps you solve problems, right? How come? Well, as theta goes to 0, it approaches 1. That's one good thing about it. But anyway, what happens when tau is really small? When tau gets smaller and smaller and smaller and smaller? Then the pulses in x, if you keep t0 fixed and you reduce tau and preserve the renormalization that keeps the average value to be 1, so you keep t0 fixed and reduce tau and keep the renormalization. So a0 equals 1. What happens? What happens to these things? If you look at the formula for ak, what does it reveal? Well, let's write it down over here. It's going to be sine k pi f0 tau divided by k pi f0 tau. F0 is fixed, tau is shrinking. With the argument of the sine in the numerator is k pi F0 tau. When tau is really small, there are going to be more and more k values that make that argument really close to 0. So tau really small, say 10 to the minus 59th, implies there's a wider range of k values that make k 2 pi F0 tau close to 0. Now, what does it mean to make k 2 pi F0 tau close to 0? It means you're having a sine theta over theta thing going on where theta is close to 0. And this is the same as saying there's a wider range of k values that make, and remember, this is the formula for AK, that make AK close to 1. Because when theta is close to 0, sine theta over theta is close to 1. So what does this mean? If you reduce tau, you're making the thing spikier and spikier and spikier. What you're doing is you're flattening out the spectrum in some sense. You're getting a wider and wider range of k values where the Fourier coefficients are close to 1. So that means that fixed t0 reducing tau leads to spikier x of t, in some sense, leads to a flatter Fourier spectrum. I'll put that phrase in quotes, and because we haven't really talked about the spectral representation of these signals. It's pretty obvious what we're going to do, but just so you know that. OK, so that's just some intuition there around the Fourier coefficients. Nothing numerical or anything here. It's all very qualitative, but it's important intuition, to think about that. All right, now I want to talk briefly about what level of reasonableness we need to require of x of t to enable this whole Fourier theory to go through, and how that guarantees that the series converges, and in what sense the series converges. So here's a quick dose of sort of analytical stuff. OK, we said that x of t has to be a reasonable periodic signal, fundamental frequency f0, fundamental period t0. What does that mean? So how reasonable does x have to be? So to make the Fourier series theory work, there's this list of conditions on x of t. First of all, x of t doesn't have to be continuous. It can have jumps in it, right? Like square wave we saw, or the pulse train, that had jumps. So it doesn't have to be continuous. It can have jumps, but it can't have zillions of jumps. Well, obviously it's going to have an infinite number of jumps if it has any at all, because it's periodic. But they can't be like packed in together, or whatever. And it doesn't have to be differentiable, obviously. If it doesn't have to be continuous, it doesn't have to be differentiable. And the triangle wave, that one is OK, and that one is continuous but non-differentiable, whatever. So there's going to be some complicated things. We need at least to have x of t be reasonable enough to do these integrals, for the integrals to exist. There's a list of conditions called the Dirichlet conditions. And these conditions, no one's going to hold your feet to the fire on this, but I just want you to know that the so-called Dirichlet conditions And Dirichlet is a name that's going to come up later in the class when we talk about things like sampling and windowing and all that kind of stuff. So first off, x of t is continuous except possibly for some jumps. And you know, sometimes people laugh, like, what? Continuous except possibly for jumps? Aren't you saying it's continuous unless it isn't? No, because we've already seen a function that is so discontinuous that it doesn't even have jumps. It's just something worse than that. It's that 1 when t is rational, 0 when t is irrational thing. That's a kind of discontinuity not allowed here. Second of all, any bounded interval has only finitely many jumps. And another way of stating that for a periodic signal is there's only finitely many jumps in any period of x of t. And these conditions, by the way, apply to x of t periodic. Okay. That's another condition that has to hold. And the third condition is that in between jumps, x of t has to be reasonable in the following sense. X of t is, and it doesn't have to be differentiable. It has to be piecewise differentiable. And I'll explain what that means. Essentially, what this means is corners are allowed, like in the triangle wave, but cusps are not allowed. So corners allowed. For example, triangle wave is OK. But no cusps. And what is a cusp? A cusp is something that looks like this, where the derivative goes up and increases without bound, and then it goes up to infinity, and then it starts at minus infinity and goes up. So this is the derivative of this thing is going to look something like a tangent looks around pi over 2, like that. All right, if these conditions hold, when the Dirichlet conditions hold, first off, all the calculations of the AK go right through. The integrals converge, everything works. So the AK calculations pose no problem. And furthermore, this series, the Fourier series, sum from k equals minus infinity to infinity, ak e to the jk 2 pi f0 t, this converges for all t. What does it converge to? It converges to x of t at continuity points of x of t. So it converges to x of t when t is a continuity point. It's not a jump. So it's not a jump. At a jump, it converges to what? What do you think it converges to? Say I have a signal that looks like this, and then there's a jump in it. What do you think the Fourier series is going to converge to at that jump? Yeah. Who said it? Somebody said. Yeah, it's the coolest answer. It's the one that you wish is true, right? It converges to the mean value across the jump, the halfway point across the jump. Mean across jump. OK. And I remember the clock is slow. Let me look at my phone and see if it's 11:40 or the other end of the class. All right, so one thing I want to talk about in addition about this, the analytical stuff before we move on, is this Gibbs phenomenon. How many people have heard of the Gibbs phenomenon? Where'd you see that? What?
Differential equations.
Differential equations, yeah. Yeah, we're going to talk briefly about that next time. And so let's just leave it at that for now.